Hello everyone, and welcome to another tutorial on how to configure your HMI. Today we will go over C language and macros. Heading into the project, I have created a simple example that will make certain buttons and functions work accordingly by utilizing macros. First, I'll explain what we want to achieve. Imagine a village, a community far away, that needs to press a button to receive water from an existing organization. The water is sent directly to their facility. There are multiple sections in the village, and each section has its own cistern. Each cistern provides water for every house. To get water to the houses, we first need to press a button so that water from the organization arrives in the village. Then, we press another button to send the water from the village to the village cistern. Finally, depending on which house we want to send the water to, we press the corresponding button. All right, to make all this happen, we will need a bar chart, multiple meters, pipelines, numeric value displays, and buttons. Let's start by placing a bar chart to represent the water level in the village. Go to the component menu, select Bar and Meter, and then choose Bar Chart. Set the minimum and maximum values, add the address type and number, and configure any additional settings as needed. Once done, add it to the project. Next, we will select a meter to determine the amount of water in the village cistern and add sector meters to represent the houses. Again, go to the component menu, select Bar and Meter, and choose the component you need. Set the limits, select the appropriate address and address number, and configure any additional graphics. This part is straightforward. Once all the components are in place, you can decorate the space however you like. You can add static text to describe the charts, numeric value displays to show values clearly, and pipelines to represent the flow of water. To add a pipeline, select the Pipeline component from the menu. You can set the direction, diameter, and size, among other properties. The purpose of the pipeline is to display an address type and number, so that when a button is pressed, the water flow is represented accordingly. Now, let's move on to the macro. Select Create Macro, and a pop-up window will appear. I have already created a macro, but I'll explain how we got here. First, on the left side, we are going to create alias names for each of our addresses. Aliases are used to make the code more readable and maintainable. Instead of hard-coding addresses, you use meaningful names. Select Create Address Alias for the specified bit address. Choose between a bit address or a word address. Select the device you are using, which can be a local register, PLC, or any other device. Add the address type and address number, then press OK. You will now have an alias specified for the address you will use. Let's add some more addresses. Now, let's implement the code. At the beginning, we include the macro library and declare the int macro main function. This line declares the start of the macro main function. With the aliases set up for the specific addresses, let's read one bit from this address. To do that, start by selecting the read-write function and choose GetBit. At the top, write inside the read-write function. At the bottom of the page, you will have bool, GetBit, address alias, and address offset. Let's start with the read bit register. The address alias specifies the base address of the register from which the bit will be read. This alias will represent the bit register. The address offset specifies the offset from the base address. The offset is added to the base address to calculate the target address. For example, if our fill tank is LB1 and we set an offset of 5, the target address will be LB1 plus 5 equals LB6. You can add this offset using a constant or a variable. The return name declares a Boolean variable to store the result of the getBit function. Bool is a data type that can hold one of two values, true or false, 1 or 0. The variable name will store the value of the bit. Let's add more of these getBit functions. For example, fillTank is the alias for LB1, so the getBit function will read the bit value from LB1 and return it to the BOOL variable power. Now that we've established getBit, let's move on to GetWord. It's pretty much the same. But this time, instead of using a bit address, it is specifically designated for word addresses. Let's add every single address we will use. The alias water tank represents the register LW10 in this example. So the target word register is LW10, and it will return an unsigned short variable named C. Next, we have the getDword function, which reads and returns a 32-bit double word value from a specified register address with an optional offset. The function unsigned int getDword, say address, aliasy, address offset, reads a double word, 32 bits, from a specified register address. The @address alias parameter represents the starting address register, which can be a word or double word, and the address offset is an unsigned integer, indicating the offset from this address. The function returns an unsigned integer with the value of the double word read, combining two consecutive words if the address type is a word. For example, if we use the alias house1, which represents the register LW91, the target word registers are LW91 and LW92. These two values would be returned to an unsigned int variable named x. The float getFloat, address, aliasc, address offset. Function reads a single precision floating point number from a specified register address, the address. Alias parameter selects the starting address register, which can be a word or double word, and the address offset is an unsigned integer indicating the offset from this address. The function returns a float value that is stored in the double word register or two consecutive word registers. The int getMem, array pointer, at address, alias address offset byte number. Function reads consecutive words from specified registers into a predefined array. The array pointer points to this array at address. Alias selects the starting register address. An address offset specifies the offset from this address. The byte number determines how many bytes to read, calculated as the size of the array element type multiplied by the number of elements. The function returns an integer, 1 for success, 0 for failure, and -4 if the call fails. The getMem function efficiently reads multiple consecutive registers into a predefined array, making data management more concise and streamlined. The GetMemEx function reads consecutive words from specified registers into a predefined array, allowing for different data types: data int 16, data int 32, data float, making it versatile for various data management needs. The GetMemEx function is used to read consecutive words from specified registers and store them in a predefined array. It takes several parameters: an array pointer, which points to the memory where the retrieved data will be stored; an address alias which specifies the base register address to read from; an address offset, which is added to the base address to determine the actual starting address; the number of bytes to read, which must match the size of the array elements multiplied by the number of elements, with a maximum limit of 20,480 bytes; and a data type, which can be data int 16, 16-bit integer, data int 32, 32-bit integer, or data float, 32-bit floating point. The function returns 1 on success, 0 on failure, and -4 if the function call fails. For example, if unsigned short data 10 is used as the array pointer, and GetMemEx data, array data I, 2, 10 times size of unsigned short, data int 16 is called. The function reads 10 words starting from LW2, assuming our array data I and G LW0, and stores them in the data array. In another case, if a char array of size 5 is used, char data, with GetMemEx data, array data I, 2, 5, data int 16, the function will read 5 bytes, which requires reading 2 bytes. 3 words, since each word is 2 bytes. The higher half of the last word will be unused. The function dynamically determines the starting address based on address alias and address offset, and ensures proper memory alignment for different data types. The setBit function is used to set a specific bit at a designated register address. It takes 3 parameters: address, alias at, which represents the base register address, where the bit is to be set, an address offset, which is an unsigned integer added to the base address to determine the exact bit location, and a set value, a Boolean, 0 or 1, that specifies whether to clear or set the bit. The function returns 1 for success and 0 for failure. The SetWord function is used to set a 16-bit short value at a specified word register address. It takes 3 parameters, at address alias at, which represents the base word type register address, where the value is to be set, an address offset, which is an unsigned integer added to the base address to determine the exact word location, and a set value, a short type value that will be stored in the designated register. The function returns 1 if the operation is successful and 0 if it fails. Since we will be utilizing this function, let's add a couple to our code. For example, the alias water tank refers to LW10, so the function will set the word register LW10 to the value of C. The SetWord function is used to store a 32-bit int value at a designated register, which can be a double word dword register, or 2 consecutive word registers. It takes 3 parameters, at address alias at, which specifies the base register, word or dword type, an address offset, an unsigned integer added to the base address to determine the exact location, and a set value, an int type value, that will be written to the specified register. The function returns 1 for success and 0 for failure. The setFloat function is used to store a single precision 32-bit floating point number in a designated register, which can be a dword register or 2 consecutive word registers. It takes 3 parameters, at address alias at, which represents the base word or dword type register, an address offset, an unsigned integer added to the base address to determine the exact register location, and a set value, a float type number that will be stored in the designated register. The function returns 1 if the operation is successful and 0 if it fails. The setMem function is used to write data from a predefined array into consecutive registers starting from a designated memory address. It takes 4 parameters, array pointer, which is a pointer to the array containing the data to be written, address aliasy, which specifies the base register address, bit type, or word type, address offset, an unsigned integer added to the base address to determine the actual starting register, and number of bytes, an unsigned integer that specifies how many bytes should be written, with a maximum limit of 20,480 bytes. The function returns 1 for success, 0 for failure, and -4 if the function call fails. The setMem function is also used to format and write an array of characters, a string, into a contiguous block of word-type registers starting at a specified address. The function takes several parameters, at address, alias at, which specifies the base address of the target register. Only word types like LW or MW are supported. Address offset, an unsigned integer that is added to the base address to determine the starting address for writing. Encoding format, which defines the text encoding used. Options include UTF-8, UNICODE, or GB2312. Array pointer, a format string containing placeholders for dynamic values, e.g., range %d, overwritten from value %d to 0, and a variable number of arguments that correspond to the placeholders in the format string. The format specifiers supported are %d for signed decimal integers, %x for signed hexadecimal integers, %f for single precision floating point numbers with 2 decimal places, %c for characters, %s for strings, and % to represent a literal % character. The function returns an integer indicating the result, 1 for success, 0 for encoding errors, and -4 for call errors. In the system functions, there are more functions that will be useful to implement. The CallMacro function is used to execute a designated macro by its name. The function takes a single parameter, macro name, which is a string specifying the name of the macro to be called. It is important to note that the macro name should not include any file name suffixes, e.g., .cppi or .h. The function returns an integer value, which corresponds to the return value of the main function of the called macro. This allows you to capture the result of the macro's execution and use it for further logic or error handling. The GetError function is used to retrieve the error code from the most recent operation, particularly in scenarios involving communication with external devices like PLCs or other hardware systems. This function does not require any input parameters. It returns an integer value that corresponds to a specific error code, providing insight into the status or outcome of the operation. The possible return values and their meanings are as follows. 0. Not executed. The operation has not been performed or initiated. 1. Success. The operation completed successfully without errors. 2. Timeout. The operation timed out, indicating that a response was not received within the expected time frame. 3. Error. A general error occurred during the operation. 4. Socket word error. An issue related to socket communication or word alignment occurred. 5. Communication failure. A failure in communication with the external device or system. Many of the read-write functions have GetError in their descriptions. Feel free to ask any questions in the comments if you're still having trouble with this. The delay function is used to pause the execution of a program for a specified amount of time. The function takes a single input parameter, which is an unsigned integer representing the number of milliseconds to delay. For example, if you pass 1000 as the parameter, the program will pause for 1000 milliseconds, 1 second. The function does not return any value. The setComm function is used to configure the communication parameters for a specified COM port, enabling serial communication between devices such as PLCs, HMIs, or other hardware systems. This function takes 6 input parameters. The port number, which is an unsigned integer representing the COM port ID, e.g., 0 for COM1, 1 for COM2, 2 for COM3, and so on. The baud rate, an integer specifying the communication speed in bits per second, BPS, with common values including 9600, 19200, 38,400, 57,600, and 115,200. The data bit, an integer defining the number of data bits in each frame, which can be either 7 or 8. The stop bit, an integer specifying the number of stop bits, which can be either 1 or 2. The check bit, a character or integer defining the parity check method, with valid options being N or 111 for no parity check, O or 111 for odd parity check, and E or 101 for even parity check. And the communication mode, an integer specifying the communication mode, with valid options being 0 for RS-232, 1 for RS-4, 854 wire, and 2 for RS-4, 852 wire. The function returns an integer value, 1 for success, and 0 for failure. The output function is used to send data through a specified COM port. It takes 3 parameters: port ID, which specifies the COM port, e.g., 0 for COM1, 1 for COM2, buffer pointer, a pointer to the buffer array containing the data to be sent, and data quantity, the number of bytes to send. The function returns the number of bytes successfully sent. For example, output 1, send buff. 12 sends 12 bytes from the send buff array through COM2. The import function is used to receive data from a specified COM port. It takes 4 parameters: port ID, which specifies the COM port, buffer pointer, a pointer to the buffer array where received data will be stored, buffer size, the maximum number of bytes to read, up to 4096, and timeout limit, the maximum wait time in milliseconds. The function returns the number of bytes read or -1 if an error occurs. For example, import 1, recv buff 16, 10 reads up to 16 bytes into receive buff from COM2, waiting up to 10 milliseconds. Both functions require the COM port to be initialized using setComParam beforehand. This code starts by including the macro.hheader file and defines the main function macro main. Inside this function, several Boolean variables a, b, e, f, and g are initialized by reading from specific memory locations. These variables determine the conditions for filling different tanks and houses. Additionally, unsigned short integer variables c, d, h, I, and j are initialized by reading from memory locations that represent the water levels in different tanks and houses. The code then checks various conditions to increment or decrement these water levels. If A is true and the water level C is less than 100, C is incremented, and the updated value is written back to its memory location. If B is true and D is less than 100, C is decremented, as long as it is greater than 0, and D is incremented, with both values being updated in their respective memory locations. Similar checks and updates are performed for E, F, and G, ensuring the values of D, H, I, and J stay within their limits and are updated accordingly. Essentially, the code manages the water levels in different tanks and houses based on specific conditions to ensure none of the values exceed their predefined limits. Go to the Timer tab and add a timer to your project. You can modify the execution period to your liking. Then, in the timer function, click Run Macro so that the macro can be integrated within the project. Once everything is coded correctly, hit Compile, and then click on the window. A Modify window pop-up will show up. Now that we are done, click Offline Simulation to see if everything is running smoothly. And there you have it. This is how we add a macro code embedded within an HMI project.